Assalamualaikum. I welcome you all to a new lecture in NS224 numerical analysis. This is Said Ibrahim, your numerical analysis teacher. In today's lecture, we are going to start a new chapter named System of Linear Equation. Previously, we have studied a lot about it at 9th, 10th level and also at FSC level. So we will study it now a little bit in extent because there just we have studied the Gauss elimination, Gauss-Jordan method, and the many other methods like inversion method. We will study we will study a little bit more about linear equations. First of all, we need to know that why we are studying this chapter, this system of linear equations. So physically, in the physical system, typically it involves many different quantities, and the relation between that different quantities give rise to a system of linear equation. System of equation, it may be linear, it may be non-linear, but mostly it is linear equation. And one of the most important part of system of linear equation is that we can decompose a non-linear equation to a system of linear equation, and then we can solve it through. There are many analytical and algebraic methods to solve that systems exactly. So let us start from linear equations. Till now we have studied a single equation, a single linear equation, and a single non-linear equation. As previously we have studied a lot of methods like bisection method, Newton-Raphson method, secant method, and Regula-Falsi method, iterative method for a single non-linear equations, how to find the approximate solution for a non-linear equation. We have studied it. Now also at 9th, 10th level we have studied the equation of a straight line, and at FSC level, at a high level, we have studied it, a single equation, a single linear equations represent a straight line graphically. So this is a single linear equation. Now from now on we will study the system of linear equation, more than one equation. So the solution of the system of linear equation having n variable, it means if we have two variable, then we need the system of two linear equation to find the value of the two unknown variables. And if we have three variable, then we need the system of three equation. And if we have 5 unknown, then we need 5 variable. If we have n unknowns, then we need the system of n equations to solve or to find the solution of that system. So the solution of a system having n variables, x1, x2, x3 up to xn, is the collection of points x1, x2. When we substitute all these values x1, x2 up to xn in any equation in the system, it will satisfy that equation. So it will satisfy all the equations in the system. That's then we call it the solution of that system. Now coming toward the consistent and inconsistent, those systems which have at least one solution or infinitely many solutions, then we call it consistent. And if the system have no solution, then we call it inconsistent. There are three possibilities of the solution of a system of linear equation. The first possibility is the system may have a unique solution. The second possibility is the system may have infinitely many solutions, and they are also may have no solution. There may be the system has no solution. So if the system has no solution, then we call it inconsistent, and if the system has at least one solution, then we call it consistent system. Now starting from the system of two equations. So separately, when we plot the equation or having two unknown, it gives us a straight line. So if we plot both the equations, we will get straight lines. So now here, if the first possibility is if these two lines intersect each other at one point, it must be at one point if the slope is different. Then we call it that system has a unique solution. If both the lines are parallel in the system of two equations, then we say that there is no solution for that system. And if both the line coincide each other, then we call it the system has infinitely many solutions. Now we have a theorem that any system of linear equation has one of the following exclusive conclusions: A, no solution. So in A, in equation in the system of two equations, if the graphically both the lines are parallel to each other, no solution. If both the lines intersect each other at one point, then we say that the system has a unique solution. And the unique solution, the solution is that point where both the lines cross each other, and both the equation will satisfy that point, and that intersection, the point of intersection. And if both the line coincide each other, then we say that the system has infinitely many solutions, because each and every point, both the equation will satisfy each and every point. And now let us see what about the system of three system having three linear equations. So if the system has three linear equations, then there will be three unknown, and when we plot it, it gives us a plane. And when we plot it, if all three planes cross each other at one point, then the system will have a unique solution. If all the planes are parallel to each other, then the system will have no solutions. And if all the planes coincide each other, then the system will have infinitely many solutions. Carefully, in the system of linear equations, the solution of the system represent a point where that point satisfy all the equations in the system, which means that graphically in the system, each and every the graph of each and every equation will pass through that point. And previously we have studied that in a single non-linear equation, the solution or the root of f of x is equal to 0 is the point where the graph of f of x touch x-axis. So carefully note it that in a system of linear equation, the solution will be a point from where the graph of all the graphs of all the equation pass through that point. So let us take a system of linear m equations. So it will be represented as a11 x1 plus a12 x2 and plus dot 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 dot. On the right side there will be a constant b1. It may be 0, 1, 2, 3. It is a variable constant, so it may be 0, 1, 2, 3 or any other number. So the system may be of two equations. The system may be of three equations. So the system will be the relation of two or more than two equations. So now here we can write that system in augmented form. This form is called the augmented form. These all values a11, a12, up to a1n. And on the right side was b1 is the coefficients of x1, x2 up to xn in the equation, in the first equation in the system. That one is in the second equation is the coefficient of x1, x2 and x3, as we have seen previously. that so the second equation, the coefficients of the second equation will be written in the second row, and the coefficients of the first equation will be written in the first row. These all are, we have studied it previously, but I am recalling it because we need it a lot next in the next lectures. So now the coefficient matrix, that matrix is called the coefficient matrix. When we write all the coefficients of the first equation in the first row, the coefficients of the second equation in the second row, and so on, the coefficient of nth equation in the mth row, then this matrix is called the coefficient matrix. Now coming to the elementary operations, what can we do with the equation? So we can multiply any equation by a non-zero number. The second, we can replace any equation with itself added to a multiple of another equations. We will study it in the next lectures, but you need to know we have three elementary operations, and also we can interchange the order in which the equations are listed. So it means that we can write the third equation at the place of the first equation, and the first equation at the place of the third equation, so we can interchange its order. So now coming to the elementary row operations. When we write it in augmented form or the coefficient matrix form. So mostly in augmented form, we do these three operations. So we can multiply any row by a non-zero number. We can also replace any row by a multiple of another row added to it, and also we can switch the rows. Now coming towards the reduced echelon form, as we have studied previously at FSC level, that a rectangular matrix in a reduced row echelon form, if it has the following conditions. The first condition is if a row has non-zero entries, then the first non-zero entry is one called the leading entry. The first non-zero entry in the row is called the leading entry, but at FSC level we have studied it that it may be 1, so that's why I write here 1. It may be 2, it may be 3, but the first non-zero entry in the row is called the leading entry. The second condition is if a column has a leading entry 1, all the other entries in the column are 0. So if in the first row the first entry is a leading entry, a non-zero entry, then below that entry all the entries will be 0. So below and above in echelon form, the below and above the leading entry all the entries will be 0. If a row contains a leading 1, then each row above it contains a leading 1 further to the left. I will discuss it in the example. So coming here toward the example, so the first non-zero entry in the first row is 1, and below that one all the entries are 0. In the second row the leading entry is again 1, and below and above all the entries are 0. In the third row the leading entry is 1, and below and above all the entries are 0, and at the fourth in the fourth row the leading entry is 1, and below and above all the entries are 0. At the fifth row the leading entry is 1, and above all the entries are 0. So this matrix is in reduced echelon form. Now taking another example, so in the first row, now here the leading entry is 1, so below the leading entry all the entries are 0, and on the left side the third condition, now on the left side all the entries are 0, and on the left side, and from that value below, that entry below all the entries are 0. So the third condition is also satisfied here. Now in the second row the leading entry is 1, and on the left and below the left side all the entries are 0, and in the third row the leading entry is 1, and on the left and below that left all the entries are 0. So that's why this matrix is also in a reduced echelon form. So note that this entry is also called a pivot entry, and that column is called a pivot column. So let us define it. Suppose row operations are used to transform the matrix to reduce echelon form. So if the matrix is in a reduced echelon form and the position of the first non-zero entry is called, as we have discussed, that the first non-zero entry is called the leading entry, but if we convert it to a reduced echelon form, then the first non-zero entry in the row is called the pivot position, and the column containing the pivot position is called the pivot column. So in this matrix, the column 2 is a pivot column, the column 4 is a pivot column, and the column 5 is called a pivot column. Now here in this example, the column 1 is a pivot column, the column 2 is a pivot column, the column 3 is a pivot column, the column 4 is a pivot column, in the 5 is a pivot column. So now type of solutions. So if the number of the pivot column is equal to the number of the columns in the matrix, the coefficient matrix, then the system will have a unique solution. If the number of pivot column is less than the number of the columns in the matrix, the coefficient matrix of the system, then the system will have infinitely many solutions. So let us take an example. We have taken a system x1 plus 2 x2 minus x3 is equal to 1. So here we have three unknown x1, x2, x3, and we have three linear equations, so we can find the solution of that three equations. But this system will have a unique solution. Let us start how to solve it. So as we have studied, we can perform three elementary row operations. So I have started here. We have write this system in augmented form. Then we subtract below the first leading entry. We need to make these two entries 0. So what we do, we subtract 2 times R1 from R2 and 3 times R1 from R3. And then these two entry will become 0, and you need to subtract 2 times this entry from this entry, this entry from this entry, and 3 times this entry from this entry, and this entry from this entry. So recall it, second chapter matrices. So you need to recall all the concepts you have studied previously before going towards the next lectures. So after doing this, we have a leading entry in the first row, and below that leading entry all the entries are 0. And then coming toward the second row, so in the second row the leading entry is -3, but we need here we need here a +1. So we will multiply that second row by -1/3, and also we will subtract that row from that row. We will get below that 1 0. So by performing these two operations, by multiplying the second row by -1/3 and subtracting the second row from the third row, we will get this. And after performing these two operations, we will get this, and after performing the last one, we will get a reduced echelon form. So on in this augmented matrix, on the right side we have the solution of this system. So when you substitute the value of x1, x2 and x3 in any equation in this system, it will satisfy that system on both the sides. You will get the same value. If you substitute all this value in the first equation of the system, you will get 1 on the left side as well. If you substitute these all values in the second equation, you will get 2 on the left side, and if you substitute all these value in the third equation, you will get also get 1 on the left side. So these points are called the solution of that system. So also we have studied previously the inversion method. So in inversion method, we need to know about the minor and the cofactors of a matrix. So if we have a matrix and its determinant is represented by D, then each and every entry have its minor and its cofactors. Like if I want to find the minor of A12, so the minor of A12 will be denoted by capital M12, and where is A12? A12 is here, so we will ignore that column and that row in which it occur, and will write A21, A23, A31 and A33 in determinant form, and when you expand it, you will get the minor M12. So A11 have also its own minor, A13 is also, so each and every entry has its own minor. Now coming toward the cofactor, when we multiply -1 to the power I plus j with the minor, it will give us the cofactor of that entry. So also we can solve this system through inversion method. So in the inversion method, we write a coefficient matrix and a variable matrix on and also the resultant matrix. So the coefficient matrix here, the coefficient of x1 is 1, the coefficient of x2 is 2, the coefficient of x3 is -1, the coefficient of x1 is 2 in the second equation, and the coefficient of x2 is 1, and the coefficient of x3 is 4. The coefficient of x1 in the third equation is 3, the coefficient of x2 is 3, and the coefficient of x3 is 4. And we have three unknown x1, x2 and x3. On the right side we have 1, 2 and 1. So we have write it in that form. Then when you multiply to the left side A inverse, so here we will get the identity matrix, and identity matrix multiplied by x will give us again x. So we will get x is equal to A inverse B. Now first we need to find A inverse. It is the same way as we have studied it previously at FSC level. So A inverse can be found through whenever A determinant into adjoint of A. First of all, we need to find A determinant. So expanding by row 1, what will we get? We will get A determinant is equal to 1 into, we will ignore this column and this row, and 4 1s are 4, minus 4 3s are 12, minus 2 time, we are expanding by row 1, so that's why I write here minus 2 time, and the position of that entry is 1 2. So the 1 plus 2 is 3, which is odd, so we will write it negative. We will write a negative sign, and then we will write 2, and after writing 2 we will ignore that column and that row. We will get 2 4s are 8 and 4 3s are 12, minus 12, plus again once again the position of that entry is 1 3, and 1 plus 3 is 4, which is even. So we will write a positive sign, and minus 1 is that entry, so I have write it here, and then we will ignore that column and that row. So what will we get? 3 2s are 6 and 3 1s are 3, 6 minus 3. So the determinant of A is minus 3. So we will note it. Now to find the adjoint of A. So the adjoint of A is the transpose of that matrix, and in that matrix all the entries are the cofactors of that entries. So when we take a transpose, we will get A11, A21 and A31, and A12, A22 by changing rows by columns, we will get a transpose. Now how to find A11, A12, A13 and so on. So as I told you, the matrix is that one matrix. So as I told you, we will ignore all the entries for A11 in that column and that row. So we will get 1 4 3 4, and you need to write minus 1 to the power 1 plus 1 is 2. So when you expand it, 4 1s are 4, 4 3s are 12, 4 minus 12 is minus 8, and minus 1 square is plus 1. Now for a1 2 you need to ignore that column and that row. So what will we get? We will get 2 4 and 3 4. 4s are 8 and 4 3s are 12. So 8 minus 12 is minus 4, and minus 1 to the power 3. Where this 3 came from? So 1 plus 2 is 3. That's why we write in the 3 in the power. So minus 1 into minus 4 will give us plus 4. For a1 3, we will add this 1 plus 3 minus 1 to the power 4, and we'll ignore that column and that row. So we will expand this matrix determinant. So we get 3, and in the same way we will find a2 1, a2 2, a2 3, a3 1, a3 2, and a3 3. So we get the adjoint of A. So the adjoint of A is here. Now when we divide that adjoint of A by A determinant, we will get that, and after multiplying the adjoint of A with B, the adjoint of A with B, we will get the value of x1, x2, and x3. So also we can perform all these steps through by using calculator. So here we will learn the calculator coding for solving the system of linear equation. So let us see how to solve this system through calculator. With the help of calculator we can solve this system very easily by pressing the mode button. You need to press 6 for matrix. After pressing 6 button, press AC button. Then after pressing the shift button, press 4. For 1 is for dimension, 2 is for data, 3 is for matrix A, 4 is for matrix B, 5 is for matrix C, 6 is for matrix answer, 7 is for matrix determinant, and 8 is for the matrix transpose. So you can find the transpose of a matrix, the determinant of a matrix, the inverse of a matrix directly by using your calculator. Now to substitute or to assign or to put our matrix in the calculator, you need to press 1 or a dimension. Now our matrix A, for our matrix A we press 1, we will press 1. Our matrix A is a 3 cross 3 matrix, so I will press 1. So now to write or to put our matrix here, so I will press 1 for the first entry, and then by pressing equal button, the first entry will be assigned to my matrix in our calculator. By pressing 2 and after pressing equal button, the second entry also is assigned to the calculator by pressing -1, and after pressing the equal button, pressing 2 and press equal, 1 press equal, 4 press equal, 3 press equal button, 3 press equal button, and 4 press equal button. If you have made a mistake, then you can go to any entry by using that arrows and you can change it. Now after writing the matrix in the calculator or assigning the matrix to the calculator, press AC button. Now we need to write the matrix B in our calculator, so I will press shift to move 1 for dimension, 2 for matrix B. Now the matrix B is 3 cross 1, so I will press 3 button for 3 cross 1 matrix. Then we will substitute our matrix. 1 is the first entry, 2 is the first entry in the second row, 3 is the 1 is the first entry in the third row. After substituting A, matrix A and B in our calculator, press AC button. After pressing the AC button, I will press shift for matrix A is on 3. Now I want to find the inverse of matrix A and want to multiply that inverse with B, multiply by a shift 4 matrix B is on 4, then after pressing the equal button you will get your result, the solution. The value of x1 is 7, the value of x2 is -4, and the value of x3 is -2. So very easily you can find the root of a system of three linear equations using your calculator if you know the inversion method. So in inversion method we have studied that we can find it by multiplying A inverse with B. Also you can find the adjoint of A and determine the determinant of A by using your calculator. Let us see how to find the adjoint of A. For the adjoint of A you need to press on button and you need to press matrix A, and for first of all we will find the determinant of A7 is for determinant, and then you need to press shift 4. Matrix A is on 3 because we want to find the determinant of matrix A. So when you press the equal button, the determinant of matrix A is -3. Now let us see how to find the adjoint of A. So by pressing shift 4 and matrix A is on 3. So as we know that A inverse is equal to the 1 over A determinant into adjoint of A. So as we have find the A determinant is -3, so -3 multiplied by A inverse will give us the adjoint of A. And after pressing A inverse, we will get adjoint of A. Let us compare it with our adjoint of A. So look at here, -8 is the first integer, -11. So by using calculator we can find adjoint of A inverse, or the solution of the system of linear equation very easily. After learning it, please try to solve this equation by using calculator coding, and after learning that coding we will learn the LU decomposition, the Krauts method, the Dirichlet method, and many other methods for solving the system of linear equations. See, any query you can contact me through my WhatsApp number, and from 9 to 4:30 I'm available on my WhatsApp number, so you can contact me anytime from 9 to 4:30. See you in next lecture. Take care. Allah Hafiz.